Good afternoon, good morning, good evening to everybody. This is our last webinar for today. Today we're going to be talking about planetary conditions for life. We have a panel here. The rest of the panel will be joining us in a short while. Francis will join us in a short while. But we can kick off. The intention is to talk through a number of important questions that the panel have selected, and NASA has selected together. The questions you can see in the bottom right-hand corner of your window there. While the discussion is happening amongst the panel, we encourage participants to join in the conversation on the open chat window to the left of your screen. You can type into there and you will see the chat happening there. My colleague David Lomas will be copying and pasting interesting and important points from that discussion into the live notes. Our intention is to run the conversation for about half an hour across the questions, and then open the floor and open the mics to all participants, so we can engage everybody in the same conversation. So while the presenters are talking, if you can keep your microphones closed with *6, that would be really useful, so we can all hear each other. So thank you very much for coming. I'd like to hand across to Michael New first to give us a little bit of context, if that's good. Thank you.
So, good afternoon, evening, morning. I'm Michael New. Those of you who don't know me, I'm the astrobiology discipline scientist at NASA headquarters. And NASA is supporting this activity. We'd like the community to really take an ownership role in it, so we're probably not going to be very involved. In the sense, you're probably not going to hear me say a lot more than this. Planetary conditions for life is one of the areas that one of the ways we think about one of the areas of astrobiology. Basically, it can be summarized very easily as how do you make planets, and once you have planets, what makes them habitable? And we can argue a lot about what habitable means. That is what we're going to talk about today. We start talking about today, and then hopefully everybody will continue talking about it in the online discussion fora that we're setting up. Participating in on this discussion and in the online discussions later on is important for two reasons. First, we're capturing everything you write, everything you say, everything you post, and so all that information is going to indirectly affect the thinking of the people who are actually going to write the roadmap. And secondly, and perhaps more direct, certainly more directly, and possibly more importantly, we're going to be choosing people to write the roadmap based on people who have active and interesting things, who are active and who have interesting things to say, both in this panel and later on in the online discussion. So I really do encourage you to participate both in the chat room here. Raise your hand. You have a function, a button on the upper left corner of your screen that lets you, if you're on the WebEx, that lets you raise your hand, and we'll call on you. And then when we decamp from this interactive presentation mode, when we go on to the discussion fora, I encourage you to start taking up questions, writing answers, commenting, because that's how we're going to move forward towards a final roadmap that will define the direction of astrobiology research for the next decade. So this is probably all you're going to hear from me today. I'm really interested to hear what everybody else has to say. So I'm just going to sit here and look wise.
You do it so well. Thank you very much, Michael. And thank you for pointing out how people can chat through the chat window and raising hands with the little icon at the top of the screen. So we'll kick off our conversation, with our panel. These questions were raised by the panel as being important topics for NASA to consider. So what I'm going to ask them to do is to tell us why you think these are important questions. Let's start with the first question, the factors determining the amount of water delivered to planets in a star's habitable zone. Stein, can I turn to you first to give us your thoughts on that?
Okay. So there's an old question within the solar system of how exactly water got delivered to the Earth. There are these isotopic inconsistencies in the water on the surface of the Earth, at least, and there's the question of what happened to the lunar impact and the water reservoir in the mantle. And I think the bottom line is we don't know within a factor of 10 what the true water content of the Earth is, or the history of its delivery. And clearly the water content is critical, at least for life as we know it. So it seems reasonable we should try to understand in detail water delivery in general, for the solar system in particular, but then also particularly given how we now understand there's a huge diversity of planetary systems. We need to understand the variability in water delivery in different contexts and for different scenarios of planet formation and for different classes of planetary systems. And we've done a little bit of work on that. Sean and I, in fact, wrote a couple of papers together, and there's several other papers that have been done in the last few years on both the astrodynamical problem of transporting volatiles within a hot disk, and a little bit on the geology and the details of delivering water through impact. There's a huge amount of work to be done, and I think even in astronomy, when you don't understand things with an orders of magnitude, and we know they're critical things, then it's a pretty good starting point to really get into some details and try to understand this properly and really try to nail this question down. And then, of course, we have to go out and get some data and test our ideas. Sean, and take it away.
Okay, I think I'm unmuted now. Yeah, I agree. This is it's an interesting question, and one thing that I find particularly interesting is we don't know that well where Earth's water came from. So there have been a variety of models of where Earth's water came from, like Stein mentioned, and the source of Earth's water has even changed over the last 10, 20 years. You know, the presumed source. And when we try to extrapolate this to extrasolar planets, because that's kind of where the next big step is, we want to think about life around other planets. I don't think we even have a good sense of which step in the process is the one that would control how much water a planet like Earth received. For example, does it depend more on the composition of the disk from which the planets form? For example, it's been argued that the carbon to oxygen ratio within the disk is a key factor to determine whether how much water you actually end up with due to various chemical reactions within the disk. Or is it the viscous evolution of the disk? Some people have argued that in many disks, if you have a very cold passive disk, it's possible that water would condense in as close as 1 AU for a sun-like star, and then you could end up having an Earth be a water world type planet typically. Then there's various other processes at play, such as short-lived radionuclides, which have an interesting story. In the solar system, there's a large amount of heat injected into the solar system at early times by things like aluminum-26 that would have dried out a lot of planetesimals. And is that a common process or a rare one? And how important is it? And then finally, there's the real formation of the Earth-like planets. Giant collisions are involved that presumably release a lot of water. Is it that the Earth tried to form with 100 times more water than we have now and only 1% remained? Or did we only lose a factor of 2 in water? That we don't really know the answer to those type of questions. So even just kind of narrowing down which chain along there governs, is the most important factor in determining the water content would be an interesting starting point. That's my thoughts for now.
Thank you. Francis will probably come back and give us some of his thoughts on this in a short while. But before we move on to our next question, just to come back to Stein and to Sean, this may sound like a very naive question, but what's stopping you making this progress already? Why is this important to be done? Why have you not made progress with this so far? Why should NASA be putting their money into this now?
Okay, I'll start again. Short answer is time, money, and people. Each of these separate problems is somewhere between a difficult problem and a near intractable problem. They're computationally hard in case of the modeling. The geochemistry is complex, and so the disk chemistry is worse because of the multi-phase chemistry, and in conditions where we don't always have lab data to get through reaction rates and kinetic equilibria, etc. And progress isn't fits and starts. You do what you can when you can, and then you hit a barrier, and you have to pause and wait for the technology to catch up or someone to put the work in to figure out the next step. And it's not just water. I see Daniel just noted that it's the whole CHON or PCHON group of elements that you need to worry about. Water is more sort of a tracer. It's got a nice moderate heat of vapor temperature at which it vaporizes, or a critical triple point. So it's a good tracker of where the ices are. It's not that it's the only unique chemical for life. It's more than a tracker for it. But personally, I find that it's literally we need to be able to have more people working on it. We need to have groups of overlapping researchers where there's continuity in the research, where it doesn't stop all the time, and it takes resources, and resources are money and people, and we're short on that. We're critically short in all these areas of people with the necessary critical skills and the amount of money to pay the people, even if they're available. So
I would add one small detail, which is that it's a very interdisciplinary question, which is why it's so relevant to astrobiology. And so, for example, when we think just about water on Earth, even to even address that problem, you have to be up to date in several different fields. So you don't just need kind of a background in geology and astronomy and dynamics and such. You actually need to be up to date because, for example, there was a new paper last year revising Earth's bulk water content, changing it by about a factor of 3 from what we thought before. There's new dynamical models all the time. There's all sorts of new discoveries in exoplanets that influence how we think they formed and even how we think the solar system formed. So to really put the pieces together, you don't just need people who have kind of a background in one field who are now doing another field. You need people who are at the forefront of each different field kind of working together, which is, I think, the advantage of astrobiology research.
And just to chime in on this, one of the problems you run into is, even if you get going on this, the research is quantized. You get maybe a 3-year grant, and then it's currently essentially a lottery whether you're going to get a renewal on that grant or not. And that makes it really difficult to keep a continuous research theme going. This is not specific to this problem. This is a general one. And I think NASA is perfectly well aware of this. But it makes it hard to maintain progress where you have to stop and try again, as it were.
Well, thank you for the response there. Does that apply also to our second question on our list here about organic molecules? Could you again explain to us in some detail as to why you think this question is important for NASA to consider?
Sean, you want to go first this time?
Sure. Well, this particular question about organic molecules and such is really not my specialty. But I mean, I think the general idea of understanding where these molecules that are key for life on Earth come from, how you can, how they're preserved and what you really need is really important, and also multidisciplinary, because it should connect naturally between kind of planetary science and geology. And even astrophysics, when you think of the abundances of different elements in the interstellar medium or in clouds that are going to form stars and planets. So I think it's a very important question. I don't know too much about the details of it personally, but it's very interesting.
So, again, I'm an astronomer, not a biologist or a chemist, but we know in the interstellar media we get part of the way there at least. We get moderately complex molecules forming in the gas phase and on solid surfaces on planetesimals in the solar nebula. And these are clearly delivered to the Earth and other planets in general. So you start off halfway there. There are moderately complex organic compounds. There are compounds we know are biologically interesting or pre-biology interesting, like amino acids and sugars we see directly in space. So what we don't know is the big step from how we get to true prebiotic or sort of protobiotic conditions. And there are some really interesting ideas out there on it. The classic tidal pool idea, hydrothermal vents, the new pumice raft idea, clays. There are a number of places where things could be happening. Maybe you need all of them. Maybe you need some of them. Maybe just one of them will do. Or maybe you're completely on the wrong track and there's something else going on. But something somewhere gave us the conditions where the concentration and the thermodynamic conditions existed for prebiotic molecules to become protobiotic, to become biotic. And once you're through that threshold and you get autocatalysis, presumably you're more or less safe unless you contingently sterilized by giant impacts or something, or a volcano opening up right underneath the tidal pool. But, and then you have to do it again. But there's no reason we can't understand this. This is not a inconceivably difficult problem. And in fact, one of the things I've been most impressed with in the last decade of astrobiology is how strongly we've converged from both ends on understanding this problem. And it seems to me that this is a very large question in science. In fact, in a lot of surveys, this is one of the two big questions that we must understand, the origin of life question, how you transit from prebiotic to biotic. And we seem to be primed to answer it, unless we're missing something really subtle. I think we are very close to really understanding step by step what's going on, even possibly down to the point of replicating it. And there have been some classic lab experiments that have elucidated some of the steps in this. And I really wish Francis were here to talk about this.
I was going to say, can I bring David into the conversation? He's raising his hand here at this point. David.
Yeah. Can you hear me?
You can.
Yes. Okay. Yeah, it seems to me that this is the hardest question of the four. It seems to me that this is really origins of life. In fact, shouldn't that question end complexification of organics towards biogenesis rather than abiogenesis? Can you hear me?
Yeah. Can you clarify the distinction?
Well, biogenesis is the origin of life. Abiogenesis is the order of something that's not life. So I just thought maybe the A should go away on that last word. But anyway, but anyway, I guess my key point is that a lot of our laboratory models can figure out parts of this puzzle, but it seems to me that the key part of the puzzle is how can we channel energy into the formation of complexity in terms of function. And so it's this coupling of the energy that's in the environment towards the increase in information content of what it is that you're trying to do that is the crux of the problem. And so I think whereas many studies have shown progress in some of the sub-areas about this challenge of origin of life, life is this system where you have the energy coupled to these complex molecules and processes. And that seems to be a tough one to me, and I don't know that there's been a lot of work done on that. So anyway, I just thought I'd say that. It's how does the system come about is the key challenge.
So I think a related question to that, and that takes us down to question 4 as well, is not just how do you couple the free energy that's flowing through the system into driving the complexification, I guess is the word we're using here, but also how little can you get away with? It sort of becomes another Goldilocks problem, because if you put too much energy through the system, you vaporize it. That does not seem to be conducive to biogenesis. Vaporizing, I go to ionized plasma if you put really huge amounts of energy through. But there is presumably some minimum amount of free energy flow where you just never get the gradients and the interesting chemistry going to where you actually get to origin of life. And again, this seems to be the sort of question where we can squeeze down to the answer. And there's presumably some lower bound of energy flow where you're just you're just not going to get there in a finite time. And some happy medium, and then the question is, are you then relying on contingent or stochastic events, or is this really inevitable? Once you get free energy flowing through a mild system for long enough with rich enough a chemistry, are you always going to get life? That's, I think, the question we want to know. And we also want to know the mechanism, or at least a mechanism, because conceivably, of course, there could be several different metabolic channels or lives, and we may be very strongly biased here in terms of what we're looking for. But at least we know we exist.
We just point out here that, as Michael points out, we're not just necessarily discussing the origin of life here, but how habitable planets are made, and how once formed they become habitable. So just to keep that on topic for the moment, can we sort of have a look towards our third question here? We'll probably come backwards and forwards across these when Francis comes back in to join us. But I just wanted to make this thing about the uniquely identifying fossils. I wonder if, Sean, could you give us a little bit of background as to why you think that was an important question to bring up?
This is another area that I'm afraid I'm not super specialized in. I know a little bit about the fossil kind of problem, like from the reported Mars fossils in the Mars meteorite. But again, I mean, this is a hugely important question of whether, even if you have a chunk of life in your hand, whether you can identify it or not. So exactly more details than that, I'm going to have to pass to someone else, given my background.
Okay, thank you. Stein, did you have something, or should I bring in David? David's got a hand there.
So David.
Oh, do you want David? Oh, okay. Well, I'm on the science definition team for the Mars 2020 rover, so I have to be a little careful about what I say here. But this is a challenge. To really get at this question, you need to figure out how to collect samples, and then, quite frankly, in the long run, get them back to Earth. And so the real challenge is, how do we intelligently select samples, and then, of course, what do we do with them once we get back? I think I would take a little issue with the latter part of that question. It's implying the absence of biologically exclusive chemical signatures, and I would think many would argue that certainly in terms of organic chemicals, there would be biosignatures that could be quite definitive. So, I think, but then of course there's the question as to whether we could ever determine them as being biological using a remote spacecraft. And I think in that case, there is reason to be skeptical that we could achieve that. But I think, at least for Mars, a key part of addressing this is the issue of sample return.
I'll try to answer this question in the chat.
A lot of people would argue that that's where Earth-based labs are going to be.
The grains, the dust grains that we sample and we recognize is crystalline.
I'm sorry, could someone clear the telecom?
Can we just do it?
The mic is open.
Might have been in the gas, the dust.
Thank you.
Sorry about that, Dave. I'm just going to have to mute that line for now, but you want to take it over again, Tim?
Thank you. So, just coming back then to Stein, I think you were about to sort of say something before David came in there, were you?
Yeah, I thought so. That was part of my job. But so I think the answer to the question is yes. We will at some point be able to uniquely identify fossils from microorganisms. Whether that'll be on the time scale that's useful to this roadmap is the hard question. I mean, clearly, if we can bring rocks back and see morphological signatures of rock of fossils that everybody agrees on, we're done. Unfortunately, people are very clever in coming up with alternative interpretations of such things, as we've already experienced. So a unique identifier will probably require cumulative evidence of multiple lines of evidence, not a eureka moment of, wow, here's the definitive single proof of life on another planet, or past life on another planet. In particular, between looking for like biosignatures and isotope ratios and signatures of metabolism and morphology, we should be thinking about what else is there. Is there something we're overlooking where we can pick up, if not a conclusive, unique identifying signature, supporting evidence, or little things that when they go together with another strong but not conclusive signature, do they cumulatively add up to a unique signature, or a convincing enough that everybody more or less can agree, okay, we really got something here. I don't know. I suspect we're going to find out the hard way by going and trying and failing a few times and then keep doing it again and again and again. But it's clearly possible, and it's interesting, and we should be doing it. Soon. I'd like to know the answer.
Thank you, Stein. We have a hand raised from David. David, do you want to join us?
Sorry to keep... a useful concept in this regard might be something called a potential biosignature, as opposed to what you might call a definitive biosignature. And the value of this concept of a potential biosignature is that this is going to be an iterative process. We first had to go to Mars to establish the extent of water activity. Now we're sort of at the level of trying to make a more complete investigation with respect to what is required for habitability. And of course, as you know, that's more than just water. And then the same thing really applies to biosignatures. We need to know where are the best places to go to get the best chance for preservation of biosignatures. And the first things we're going to see that are interesting will be potential. They certainly will not be proven. But then that helps narrow the search. And so how do we set up sort of an iterative approach to this problem to break it down into tractable steps? And so this concept of a potential biosignature, just like the Alan Hill stuff was before we came down with a more definitive determination, I think is a useful concept to consider.
What I'd like to do now is open the question to the floor, really. We have a number of questions here, which I think Francis had something to contribute to as well, but then hopefully he'll join us shortly. But the attendees, we have 27 attendees here. What are your opinions on these questions here? Why do you think these questions may be important for NASA to pursue? Why should they be on the astrobiology roadmap? If you can raise your hands, Daniel, thank you first. I'll take you.
Okay, so I would like to address the first question. I hope you can hear me now. I think that's an important question because exoplanets have been growing in importance, and they are very likely going to play an important role in next decade's NASA space missions. This question is very important because it helps, answering this question helps to figure out which are the right targets. And once we observe the targets and the planets, we can better characterize them and understand their potential for hosting life. I think, as I mentioned, I think it's important to extend the question from water to also other biocritical elements. And because the processes are very complex and some of them are stochastic that can deliver volatiles and organics, it's important to study trends and recognize the combination of these processes that needs to be understood.
Thank you. I understand that George Cody may also have an opinion on some of these. George, can I ask you if you could give us your thoughts on these questions? Sorry to put you on the spot there. George isn't there. What I would, I'd also draw. Timothy, I can see your hand up. Thank you.
Yes, hello. Can you hear me?
Hello. Yes, we can.
Yes, hi. I'm Tim Zwier from Purdue University, and I'm a chemist, physical chemist here at Purdue. And so I've been thinking particularly about this second question here about the organic molecules and how they can be produced. And it seems to me that there may be a need for some new types of laboratory-based experiments. I think this is one of the regions in which actual laboratory-based experiments could be particularly useful because, of course, chemists have built up over time an extraordinarily sophisticated set of techniques for exciting molecules, irradiating them in various ways, and then following reaction pathways to specific products. When I think about some of the work that's been done over the years, of course, much of it takes a quite different tactic where you take a pretty generic reaction mixture and irradiate it over a long period of time, either with UV or VUV radiation or a discharge or whatever it might be. And then after the fact, when the end products are formed in a film or some sort of thing, you try to characterize the final end products. But as a chemist, I would be very interested in asking specific questions about particular types of organic functional groups that are known to be present in space and pervasive, say, for instance, the nitriles or something like that, and then trying to engage in specific photochemical or irradiation chemistry that you could follow in time and specifically detect the products that are being formed to try to actually build up mechanisms then that could be hopefully general enough to be applicable in different circumstances in space.
Stein, Sean, do you have a response to that?
Yeah, I see a couple of participants who might want to respond to that. You know who you are. You got some time.
While we wait for those hands to go up, I wonder if there's anything you had to say on there. But let me just draw some attention to again for all attendees here. We're talking about planetary conditions for life, and we're wondering amongst ourselves here what things should be on this astrobiology road. What should NASA be funding? Where, if they have a huge pot of money, where should that money be focused? And we're trying to ascertain from the community what might be the best things to be having on that roadmap. So these questions here are designed to prompt thoughts. You can agree or disagree in any way you like, but all your thoughts here will be much appreciated. So raise hands, throw in your thoughts, and we can sort of discuss those further. I see that David has raised his hand. Oh, sorry, Stein, carry on.
David has his hand raised, I just noticed that.
Yes, thank you very much indeed. David, I see your hand up.
Okay, two comments about habitability. One, which we got into at the last time with this roadmap, was you have a habitable planet that can support life as we know it, and then you have the kind of planet that's habitable that could foster the origin of life. And are those two necessarily the same? In other words, could you say that the habitability of our current planet would have been the type of environment where life could have begun? And it's not clear to me at all that that's the same kind of environment. So, and especially if you believe in panspermia between planets in one system, this becomes sort of an interesting question. So that's one little distinction I thought you might want to consider in your deliberations. And the other thing, which for Mars is a big issue, is how long did these conditions persist? It's much easier to say that there was water at some time or that all the magic components that you need were present at a time, but how long do they have to be present to really make it truly habitable and especially for life to begin? So that's, to me, a key question. How can we quantify stability of the environment and persistence? That's it.
Thank you very much indeed. I think, Michael, do you have a response to that?
I have a comment. We've been talking a little bit about habitability and origin of life, and Mars, and I think that's really gotten us off track pretty far away from what I wanted us or thought we would be talking about. which are things like before you have a planet, how do you make it? Once you've got a planet or a planetary system, what makes planets habitable in that system? So, for example, we have Jupiter, and Jupiter does two things. It deflects away some material from coming into the inner solar system, but it also directs some material into the inner solar system. And that outer solar system structure of having a big giant Jupiter sitting there may be important for the habitability of the inner planets, the Earth, Mars, Venus. I also thought we'd be talking more about how organic molecules get made, where they get made in space. Do they get made in dust grains? Do they get made in ices? How do they get delivered to the Earth, too, once they've been made? So those are and that's built into these questions. And I think I would like to see more conversations, particularly, oral conversations you can hear, not just typed in the chat window, about these topics, and less about Mars and habitability. We have an entire kickoff webinar last week on astrobiology for solar systems exploration that touched on those areas, and I think posts, questions, comments on that should go to that area on the website, astrobiologyfuture.org, and let's just continue.
Thank you, Michael. And I see that Daniel has just raised a hand.
Yeah, just to follow up on Michael's point, that one of the interesting questions, I think, within the planet formation topic is how do stellar mass and binarity influence the initial volatile and organic budget of planets that form in certain systems. We know that M-dwarfs and M-dwarf planets can be very important targets in the near future NASA missions, but it's really unclear how this chemistry and the planet's volatile and organic inventory change with the stellar mass. So I think that should be part of the roadmap and one of the questions we should address.
Right. So
thank you, Daniel. Stein.
Sean, do you want to comment at this point?
Yeah, let me comment on this. So you make some good points. I mean, in terms of planet formation, it's being appreciated more and more that there are a lot of steps to get to a fully formed planet. You got to do a lot of things. You start with some little dust grains. You got to form your planetesimals. You got to make those into bigger things that are maybe the size of the Moon or Mars. Those are still, while they're still early on and there's a gas disk around, they migrate around due to the presence of the gas disk. Then the gas goes away, and then you have this kind of final sweep-up phase where you form, kind of last formation phase where you have giant impacts and form planets that are really kind of, we think, look sort of like Earth, well, at least in our case. And if you want to form a planet like Earth or a planet that could be habitable, and that's the end point, how many ways are there to make it through the chain and end up there? And that's kind of a broad view of, how planet formation connects to astrobiology. Because we don't know if you need to follow a very specific path or whether you could follow almost any path and still get, within this kind of window of a habitable planet. And there's all sorts of parameters in there, and Daniel mentioned many of them there, like the properties of the protoplanetary disk, the presence of binaries, the composition of the disk, how fast it evolves, these kind of questions. And they're big questions, and each one is being looked at individually, and some are not even being looked at yet. And connecting the dots between them with a specific endpoint, I think, is kind of an interesting way to apply this to the roadmap.
So to continue that theme, there are two issues here. One is knowing the microphysics of each step, and I think we're a long way along there, and that we think we understand a lot of the physics involved, although there may be a couple of places where there's still some physical processes where it's not clear which are dominant and which are important and which are irrelevant and can be left out of the simulations. But then, even once we know that, we're now talking about a very large parameter space, and we've kind of sampled it sparsely. Initially, we were totally focused on solar system-like systems, because that's what we had. And then as we discovered different kinds of systems, we sort of tried a few things here and there. And there's been some broad surveys trying to do a sort of core sampling of the parameter space, but we really haven't explored all these different channels. And it's perfectly doable. It requires a fairly modest by modern research standards effort in terms of, and I think computationally we're at the point where it is doable. But there's not been a coherent effort to do that. Rather, there have been people here and there doing it for a bit and making some progress. And it's getting there. I mean, a lot of different paths that people have been working on this for decades in some cases. It's all coming together very nicely. But I mean, even at the level of just looking at something like the Kepler sampler or the RB sampler systems, which is not complete, but they're both biosystems, we have not explored even what we already know now. We have not fully probed with implications of various different configurations and the implicit channel for formation and picked up what that implies for delivery organics or the conditions on the planet. We haven't in this oral session, we haven't really talked about atmospheres yet and what they imply for habitability. We don't know yet what the full range of planetary radii are that could sustain habitability. But a lot of these are doable, and I think we can do them. What fraction of the resources to be allocated to that is, I think, up for community discussion.
Can I bring Dave? David has a hand raised. David, is it building on what Stein just said?
Well, yeah, now that Mike has slapped me about the head and told me what this telecon's really supposed to be about, let me make something which I think is relevant. And that is that, in terms of volatiles being incorporated into planetesimals, I'd gotten this impression that you get up to a certain size of planetesimal and that these things can really vary in their volatile content. And then after that, you get into this big cosmic billiard game where these planetesimals collide and that you need to go through that phase really to get up to an Earth-sized object. And given the tremendous variety of volatile contents in these planetesimals, it really seems like it's a stochastic process. And so at some point, you just have to go and look. And so I think maybe one of the key things to consider in this roadmap is what is that we can actually do experimentally or with models versus what the advocacy we would make for astronomical observation missions to look at these disks. In other words, how could this roadmap guide the balance between astronomical observational approaches versus the lab or modeling on the other side, given that there's this stochastic element in there. And this stochastic aspect was one of the major arguments for the Kepler mission, that, there's this element in planet formation, we just have to go look to answer the question. That's it.
So, cool. Could I comment on this?
Of course.
It's a good point. So why not just go look and see what these planets are actually made of? The trick is with Kepler, you get a pretty good radius of a planet, and if you're really, really lucky, then you can get some sort of mass estimate. But there's no way you can really constrain the bulk composition at the moment to the degree that we need or that we're talking about in terms of these planet formation models. For example, if you took the Earth, the exact Earth replica, and then you gave it either 0 water or 100 times the Earth's current water content, its radius changes a very small amount, below less than Kepler could detect. And so Kepler can't really feed back in that directly, unfortunately. It would be great if it could. I think it will be able to in certain situations. But it doesn't give as many answers as we would like right now.
Can I make a comment? This is Francis McCubbin.
Sure.
Please do. Who's that speaking?
Francis McCubbin. Sorry, I'm a bit late.
Francis, hello. Welcome. Yes, please make a comment. Yeah.
Okay, so one way that we might actually be able to get at the volatiles from a distance is looking at the bulk planetary uncompressed density. Because, things like mercury that have very high density, high metal content, even if they had a lot of hydrogen, that hydrogen wouldn't make water. So we're sort of narrowing in on a certain core size that correlates with oxygen gigasity that allows for the stability of water, at least the prediction of the stability of water versus something like H2 that might not be as good for life. So there may be creative ways about going about, at least making predictions from afar.
Thank you very much indeed. Francis, how much of the conversation have you been able to hear so far?
About the last 10 minutes.
Okay. I'm going to turn to Daniel and David in a minute. They have some comments to make, but if you would like to have a think about some of the questions that we put on the opening slide, I'll turn to you in a few moments to give us your thoughts on why these are very important questions and why you, with Stein and Sean, decided that NASA should consider these questions. So I'll come back to you in just a moment, but let me go first to Daniel, who's got his hand up. Daniel, did you have something to build on that?
Thanks. Yeah, I just wanted to highlight some of the points that were raised, which I agree. I wanted to add that not only we have samples from Kepler, but this is the time when almost becoming
So I'm just going to mute that telecon real quick. It sounds like there's a fire alarm in someone's building.
It did.
That's a good point to bring up. We'll record this talk so you can escape the fire and watch it later if you need to. I'll try to unmute it. If it's beeping, I'll mute it again and send it back to you, Tim.
So do we still have Daniel?
Yeah, okay. So I was.
Yeah, sorry. Carry on.
Yeah, I was pointing out that ALMA is becoming functional now. We are seeing exciting results, and that gives us an opportunity to study protoplanetary disks, planetary systems in the making. And there are also observations of planetary systems or asteroids around white dwarfs, which give us another interesting perspective into the composition of planetary systems. So I think not only the exoplanets can be directly studied, but also forming planetary systems, and which I think is an important point. The other issues or opportunity here is also the process is stochastic, but I think it's important to focus on trends, because we do expect trends with, for example, stellar mass, UV radiation, etc. in the chemistry. And even if we probably won't be able to determine and predict compositions for individual planets, we should be able to come up with a statistical description for volatile budgets. And that's something that I think with the emerging new data should be possible in the next 5 to 10 years. Thanks.
Thank you, Daniel. David, you have your hand raised as well.
Just a quick comment in response to what Sean had mentioned, and that is I wasn't so much focusing on what we should do with the Kepler data, but what this group could do to advocate for a future mission. And I think that the comments you just heard before mine that got at that is, what can we do to influence the next kind of mission that would get into the types of observations of early disks that would be most relevant to this. That's it.
Thank you. Can I come back to Francis then, please? Francis, thank you for joining us as well. Still in the airport somewhere. We started the conversation going through these opening panel questions, and Stein and Sean and the participants were exploring as to why these are important questions for NASA to explore. I understand you're very much into the organics side of things. We'd be very interested to hear your comments on why these are important questions in the last 5 minutes or so.
Okay. So I guess I'll start with the first question. What factors determine the amount of water delivered to planets in the star's habitable zone and the availability of that water for participation in chemical reactions? So there's abundant hydrogen in most planetary systems, the most abundant element in all stars, really. But hydrogen alone isn't what we need for life in a lot of organic molecules. It's water. So understanding the availability of that water and how it's able to participate to make organic molecules is fundamentally important for understanding the origin of life. For example, the moon is now known to have a lot more water or hydrogen than we previously thought, but it doesn't necessarily make it a higher target for looking for life. So it's the water is sort of locked. It's too reducing, so it's hydrogen is a stable phase instead of water.
Thank you.
Yep.
And tell me more about what your thoughts are on the organic molecules.
Well, it seems that at least what we observe, we find organic molecules in a lot of carbonaceous chondrites. We're finding organic molecules within igneous minerals that seem to have formed during the cooling of magmatic systems on places like the Earth and Mars. So it seems like planets and early on in the solar system, we were able to make a lot of these organic molecules, but most of them are fairly simple. And they're typically around in minor concentrations. I mean, in carbonaceous chondrites, they're much higher, but when we find them in the context of planetary bodies, their concentrations seem to be very low. However, to get, what geologic processes, we need to understand the geologic processes that can bring these molecules together and help them become more complex so that we can move towards understanding, how and where to look for the origins of life on planetary bodies. And I apologize if I'm sounding a bit out of it. I just got off of a transatlantic flight.
Well, thank you for joining us. We are very interested in your comments on this. So if you don't mind bearing with us, we will do that. I'll also invite attendees and the rest of the panel to join in on the conversation. If people want to raise their hands, they can comment against what you're saying. As I'd just like to mention to the audience, to the attendees, we're coming just up towards the end of this conference, but as Francis has joined us in the last few moments, and he's put a lot of effort into that, I'd be grateful if we could just carry on for just a few more minutes, just make sure that we've covered everything that Francis can contribute, considering his tiredness as well. If people need to drop out, then please do. Just to make it very clear, the conversations that we are having here will be transcribed and put up onto the website in the next few hours, so the conversation can continue. And we encourage everybody to come along to the website, join in the conversations, and help us build this roadmap that NASA are trying to put together with the help of the community. So please stay engaged. Now, having said that, I'd like to just carry on just for a few more minutes, if you can bear with us, Francis, to just give us a little bit more of your insight, and I invite other people to join in the conversation with you as well. One of the questions we didn't cover, Francis, was the question right at the bottom: is life a chemical consequence of thermodynamics, or did it emerge in spite of thermodynamics? Again, why is that an important question for NASA to consider?
I think that question kind of ties into the whether life emerges from stochastic processes or whether it's an eventuality. So a planetary body largely is going to evolve. It's a very dynamic process, but it's going to evolve based on thermodynamic principles. But every now and then you get these stochastic processes, things like the late heavy bombardment, or things that really add a lot of flux to the system that throw it out of equilibrium, or at least the equilibrium that it was heading towards. And life in general is sort of a mix of equilibrium and disequilibrium processes. And so if life is a chemical consequence of thermodynamics, then perhaps we should expect to find it everywhere. If it emerges in spite of it, it may lean more towards, stochastic processes sort of inducing it because of being drastically out of an equilibrium that we were heading towards initially.
And what is the experiment? What is the research that needs to be done to answer this question?
Yeah, I guess if we could produce an experiment in the lab that turns non-living material into living material, that would really be it. But we haven't been able to do that yet. But perhaps we, should invest more in actually trying to do that and think through the chemical reactions that would actually lead to life.
Mm-hmm.
If it is a consequence of thermodynamics, then we should be able to reproduce it in the laboratory, given the right chemical conditions.
David, I see you have your hand raised.
I'll try to keep it concise. I think the thermodynamics plays a role because the approach to thermodynamics releases energy. Gets it back to that earlier discussion we had about coupling energy to these processes that we think are essential for life. So, yeah, it's kinetic, and it's that approach to thermodynamics that is the landscape, and so experiments that incorporate that, I think, are relevant. That's it.
Stein, Sean, do you have something to add to the thermodynamics conversation?
I think we need to know this answer. I can see arguing either way. Sorry, Sean, you go ahead. I see you got your fingers on the button.
No, I was just going to say I think it's an interesting question that should be addressed, but I don't have the answer as to how to address it.
It gets back to one of these very basic questions. So,
okay,
it may not even be the right question, but it's an interesting way to start.
Thank you. Unless there are any other questions from attendees, again, I ask you to raise your hand if you'd like to say something. I think it sounds like Francis is worn out, and it's probably time for us to start to wrap this up. Just while people are thinking about whether they want to raise their hand, just to close up again, to remind you, the conversation will continue on the website. We encourage you to come there and join in. There'll also be a YouTube video of this conversation, so you can see it in its entirety. And also the other themes and discussions that have happened over the last couple of weeks. They are also, again, we encourage you to step into those other themes as well, because there's quite a lot of cross-conversation, cross-theme topics and questions. So please join in. I don't see any more hands raising. Stein, Sean, did you need to wind up with anything there? All done? In which case, I will say thank you very much to everybody for attending. Thank you very much to the panel. Thank you to Francis for popping in towards the end and giving us your points on it. Much appreciated. We'll finish here. And from my point of view, have a lovely evening. Thank you. Bye-bye.
Thank you.